that way. And let me see if there's anyone else. Not that I see so far, but there's, people are still coming in. And while you're coming in, let me see if I get my OneNote running. That looks good. Okay. So my OneNote is up. This is a picture that, pardon me, has nothing to do with this class. So let me go back and see where we were. Okay. So this is something we did the other day. That was the algorithm. Yeah, this was the algorithm for finding a stationary and therefore often a steady state distribution for a Markov process. And we did it on the previous example and it worked out. And then we did the monster. Let's see if I still have the monster here. Yeah. Okay. This was the homework problem. I don't remember if this happened partly in class. I think it was partly in class or partly in the office hour, but there were people who were getting this answer. So this seems to be the answer to this homework problem. How does that resonate with you? Did you get it?
Yeah, it was in office hours.
Oh, it was office hours, but
yeah, but I did it and I got the same answer.
Wonderful. That's good. For those who weren't in office hours, you might want to jot it down just to see if you got it the same answer. Yeah, we used the algorithm because it was too big, right? It was 5 by 5. And so we avoided doing it by hand and using the algorithm. It came out to this sort of non-obvious answer, right? Any questions on the monster or the solution using the algorithm? If you need to see the algorithm, let me know again. Algorithm's not in the book. So the algorithm is stuff I bring to class. So any questions on this part? Okay, so I think this is, so after doing this, I think we didn't have any questions. So I asked the few students who were there the other day, would they like to see a preview of what today's lesson would be about? And they said, sure. And that's when I did this stuff. And so let me do that again, presuming you weren't in the office hour. So this turns out to be a result in our textbook, page 92, equation 22. So hopefully you have the book. And if you got the book electronically or physically, whatever, if you look on page 92, you'll see this differential equation. Yes, exactly as written here. So you have the derivative of function is equal to some constant, which is called minus alpha in this game, times f of t plus g of t. F of t and g of t are two functions of time. And usually we assume that both of these functions are differentiable. The alpha is a constant. And if you were to swing this term to the other side, it would look like this. So this box equation is virtually the same as this one, just with this term switched to the other side. And you might have seen it somewhere if you wanted to call, instead of f of t, the function, if you wanted to call it y of t, you might have seen it look like this, or even like this. Now let's see. Let's actually push my luck and see if I can erase something here. Yeah, okay. So if you suppress the dependency on t, which means hide it, you get dy dt plus alpha y equals g. And sometimes this has a name. It's often called the linear constant coefficient differential equation. And it has a solution which your authors go through, and I went through it last time in office hours, and I'm happy to do it again. But perhaps before doing this, you should probably check, or yeah, it's a good idea to check wherever you learn differential equations. In your first exposure to the topic, this probably was covered. Why? It's a standard result in any first course in differential equations. And you can tell from the title, well, it's actually a little more. It's first order, which means it has a first derivative only. Linear, which means it looks like something times f prime plus something times this. And then constant coefficient is the alpha differential equations. Sometimes they might even throw in the word non-homogeneous. Homogeneous would mean the right side of the equation is 0. And since it's not 0, you could. So if you want to get blown away by the words, it would be first order, linear, constant coefficient, non-homogeneous differential equation. Do you need to know all the words? No. But do you need to know how to solve the equation? Yeah, probably. So here's a common method for solving this. And sort of the key is this first step. You multiply this equation by e to the alpha t. Remember, alpha is just a constant here. Okay, so when you do that, I'm back in the f prime form here. So you get e to the alpha t times f prime of t plus alpha e to the alpha t times f of t equals e to the alpha t times g of t. So basically multiply this equation through by e to the alpha t. And here's sort of the key observation. These two terms would be what you get if you took the derivative of this product. That is, if you apply the product rule to this, how would that go? It would say take the derivative of the first factor, which is f prime of t up here, times the second factor unchanged, e to the alpha t, plus the first factor, which is f of t, times the derivative of e alpha t, which would be itself, times the derivative of the power, which is alpha. So I've just checked that the derivative of the product here is exactly what's on the left side of this equation, and the right side hasn't been changed at all. Okay, so what we do next, so that's sort of, if you ask me why do we multiply by this guy, it's because somebody already foresaw that the left side would be the derivative of the product of this and this. So that's like a key observation. The thing you multiply by to make the equation solvable is often called an integrating factor. So you may have heard of that phrase before. And coming up with integrating factors is a whole portion of differential equations. If you can come up with integrating factors, it makes it easier to solve. Okay, next step. Well, before I do next step, any questions up to this step? Okay. Replace t everywhere with s. And you'll see why in a moment, but there's no harm in doing that. Replace every t here with an s. And then integrate both sides with respect to s. Well, you're integrating this stuff with respect to s, and you're evaluating it from 0 to t. And that's really why we changed t to s, because we want s to be the variable of integration, and we want t to be the upper limit. And it's not good practice to have the variable of integration be the same as the upper limit, because this is not, the variable inside here is not a real variable. You can't set s equal to 2. It's more a symbolic variable, whereas the variable outside, you can set equal to different values or numbers. Anyway, integrate both sides from 0 to t, still get a new equality. But when you integrate a derivative, you're back to where you started, because those operations undo each other. So you just get f of s e to the ts, oh, I'm sorry, e to the alpha s, that should be, evaluated between these limits. And on the right, you get this, which we can't integrate because we don't know what g of s is. So we just leave it in that form. Okay, we can evaluate the left side of the equation. When you put s equal to t, you get f of t e to the alpha t. And then you got to subtract off what you get when you put s equal to 0. But when you put s equal to 0, you get e to the 0, which is 1. And you get f of 0. So you're just subtracting off of f0. And the right side doesn't change because, as I already said, you can't integrate it because you don't know what g is. G is some function. But now you have an equation that involves f. And that's what you're trying to find. You're trying to find the function that makes this equation work. So you've got this equation here. You swing the f of 0 to the right side, which is done here to here. And then you multiply through by e to the minus alpha t. That gets rid of this on the left side. And here, when you multiply by e to the minus alpha t, it just appears in the first term. And here it appears in front of the integral. You circle this and you are done. This is a solution of this linear constant coefficient differential equation up here. Okay. Let me just touch base with you. So I'll stop sharing for a sec. How many people have seen this formula before? Or maybe you don't remember the formula, but how many of you at least remember solving the first order linear constant coefficient differential equation? Okay, I'm getting a thumbs up from Alejandro. Do any of the rest of you remember doing this? Or looks like Virginia says she remembers it as well, or at least remembers doing it. I'm not even saying do you remember the answer, but at least remember that you covered this somewhere in your.
That's exactly me.
Yeah. I don't think it's just you. I think there's a lot of people who won't remember this. To be honest, I don't remember the equation. I do remember the procedure, so I could rederive it. So, but all I'm asking is, do you remember doing this someplace, or you've been there before? Not that you know how to get there again.
Mm-hmm.
Yeah. Well, okay. The rest of you aren't even saying that. Okay. So probably it's a good idea to have done it. And I'll give the authors credit in the book. They do it on the page. And that's, you might be wondering, well, how much differential equations are you going to have to know now? And the answer is, well, at this point, let's just keep track. There are two ideas that you need to know. The first one we've already used, and that's separation of variables, where you get all, t on one side and y on the other, and integrate and solve for y. So there's that method. And now there's this one. Will there be more? There may be one more. But right now, I think we can go with these two as what we need to push the ball along. Okay, since I'm here on this page, let me just see if is there anyone here who I didn't give permission to record? I think Miles might be one. Let me see if he's, yeah, let me give you permission, Miles. I'm not sure I could give it to Virginia. No, I guess I did.
Yeah, I got it. Thank you.
You're welcome. Was there anyone else I missed in terms of giving permission to record? Okay. Well, all right. So let's go back to where we were. And before going further, I'm going to ask you to take a couple minutes if you don't mind. I think you got an email talking about student evaluations for all your classes, probably. And if hopefully my class was included there. So let me stop this for a second again. Stop sharing. So give me a thumbs up if you got the email about doing a student evaluation for your classes. Okay, Alejandro says yes. Virginia says yes. Candace. Okay, and I'm guessing, yeah, and more are coming in board too. I don't know if you have done it or not, but I'd really appreciate it if you would. So I'm going to give you like whatever it takes, 3 to 5 minutes, I'm guessing, to do the student evaluation and submit it. By the way, it's probably a good thing if you got the time to do it for all your classes. Probably more important for the younger faculty, junior faculty, because they could be, evaluated and people look and see how their student evals look. For someone who's at my stage, it's a little late, but they can look at it too to make sure I'm doing my job. So it does have some importance. It gives you a chance to give some feedback to people. So if you don't mind, take a couple minutes at least and just take care of that now. So I'm giving you class time to do it. I believe there's like 15 questions if they haven't changed it, and I don't think they have. And there are some questions that you could even mark not appropriate if you feel it's not appropriate. When I did this in person, I always like to ask people for other input. And I used to ask that they'd write that on the back, even though they give you directions not to do that. I won't do that now because I don't get them physically. I get the results, but I don't see the actual forms. But if you do have something that you really like or don't like about the class, you're certainly welcome to email me that. And well, I guess it goes without saying, but maybe I'll say it. I'm not going to hold it against you. I'm just trying to find out how to improve the course. Well, okay, I didn't give you much time, but I hope it's enough time to at least have done it. By the way, if you were not able to do it, either you couldn't get to your email or something, you have time. It's not due until after Thanksgiving. I'll probably remind you one more time, but I do encourage you to do it. Not only for me, as I say, but probably for most of your classes. Okay, so let me go back to the math. So what we want to explore now that we have an extra tool for finding solutions of differential equations, we want to go back to, let's see. Yeah, this is, and I guess I did this in office hours as well, so I might as well make sure it's all good. So I think I did this example in office hours. Let me flip my furniture around here a little bit. because I'm going to be using the OneNote more. So here was the example that I explored or started to explore in office hours on Wednesday. Suppose you had a pure birth process. So there's no rates going down, there's just two rates going up, and they both happen to be the same. And what I wanted to figure out, well, we wanted to go back to either the forward or backward equation. And this was the one I looked at. So let me redo this a little bit. So originally, I just put in a 3x3 guy. So this would be 1, 0. This would be 2, 0t. And this would be 2, 1t. And this would be 2, 2t. So this has three states, and therefore the transition probability function matrix is this thing. And going back a little further, the Q matrix would have values that look like Q00, Q01, Q02, Q10, Q11, Q22. Whoops, that should be 1, 2. And Q20, Q21, and Q22. So that's how the three-state general Markov process would look. And this is its forward equation. So the objective would be to solve for this matrix here, P of t, before you differentiate. And we already know how these rates translate. So if you're going to go from 0 to 1, that would be this rate over here. So this would be lambda. And you can't go from 0 to 2 in one step. So Q02 would be 0. But we remember for the Q matrix that the row adds up to 0, each row. So Q00 would be minus lambda. So let's just repeat that. The rate going from 0 to 1, we call lambda. That's sort of the customary way to call a rate going up. You can't go from 0 to 2 in one step. There's no arrow going directly there, so that's 0. And then this would have to be minus lambda, so the first row adds up to 0. Now let's do the same kind of business on the second row. If you want to go from 1 to 2, that would be this rate. But that's the same rate as what we were assuming from 0 to 1. So this is lambda this time. Same lambda as before. But it's pretty clear from 1 to 0, you can't go there. There's no rate at all. Or if you want to think of it, the rate is 0. So if that rate is 0, this entry here would be 0. And then again, row 2 sums up to 0. So Q11 has to be negative lambda, so that the second row adds up to 0. So I'm sort of explaining how to get a simpler version of the Q matrix from the diagram. Okay, let's look at the last row. Well, there's no way to get from 2 to 0. There's no arrow there, so that would be 0. Nor is there any way to get from 2 to 1, so that's also 0. And the last row adds up to 0. So that means the last rate here has to be 0. Okay, so corresponding to this pure birth process, it's only birth because there's no death. No going down, only going up. Has this as its forward equation, where the Q matrix is this. Any questions on that? Okay. And then I think I did next, well, I mean, in theory, there would be 9 different functions to get here. But it's pretty clear, since you can't go from 2 to 0 in any manner, the chance of going from 2 to 0 in any amount of time will always be 0. Because there's no death rate. So this will be 0, no matter what time element you're looking at. Because you can't go down, you can only go up. Similarly, to go from 2 to 1, you can't do, there's no rate going down. So that's also 0. And we know that the rows of this matrix add up to 1. And since the first 2 entries here are 0, the last entry just has to be the constant 1. And that makes sense, because if you get to 2, there's nowhere else to go, so you just stay there all the time. So we don't have to solve for the last row because of the reasoning I just went through. And then what about the second row? Well, if you're trying to get from 1 to 0, there's no way to go down. We've already said that before. So the chance of going from 1 to 0 in time t will still be 0. So what's the conclusion with these pure birth processes? Some of it we could do without much work at all. We have 4 of the 9 done without using any different differential equations, just by using the diagram and noticing you can't go down. The other 5, however, require some attention. So let's see what we can do. And here's what I did last time, and it makes sense to pick it up from this point. So let's go for P00. So if you're going to go for this entry here, what do we know? We know that the value over here is the derivative of P00. And that would be what you get when you multiply this first row by the first column. What I mean by multiply this times this second entry by second entry, third entry by third entry. Well, the last 2 entries will go away because of the zeros. And you just get minus lambda P00 of t, which is this equation here. And that equals the first entry over here. Okay, so if we want to solve for P00, and we do, does everyone see how I got this equation from the forward equations? Forward equations, you see why they're called equations, because there's more than one, right? I'm just doing the one for P00 prime of t. That's the first row here times the first column here. And if you do that, you'll get this on the right side. And I don't know why the question mark is there, but I'll erase it. Maybe the question mark is there because one could say, how do you solve it? And this turns out to be not a hard one to do. You can just replace y of t for P00 of t. It's a little simpler. And if you do that, you have dy dt is minus lambda of y, which is one of the easier differential equations. It's where the rate of change is equal to the function itself times a constant. To solve that, you can separate the variables, bring all the y's on one side, which I did, dividing by y and multiplying by dt. Then the separation of variables technique tells you to just integrate both sides. And then solve for y by taking the exponential. And when you take the exponential over here, something got lost. It should have been the exponential of what? Minus lambda t plus c. And the exponential of the log undo each other, so you just get y. And by the rule of exponents, you get this. And since c is a constant, you can replace e to the c by another constant and put it out in front, and that's what I did. Okay, so we actually have the solution. Remembering that y is p00 of t, we can substitute that in and get p0 t equals k times e to the minus lambda t. The only thing we don't know, lambda is a known constant, k we don't know. But if you let t be 0, you can figure out what that is. So when t is 0, you have the probability of going from 0 to 0 in 0 time. But we agreed to call that equal to 1, right? You're trying to get from 0 to 0, there's no time to do it. No, don't worry, just stay there. You're already there. So the probability of getting from 0 to 0 times 0 is 1. On the right side of the equation, you just put 0 equal to t, and you get e to the 0, which is just 1. So k is actually 1. So what does it actually tell you? We've now figured out what k is. K is 1, so p00 of t is equal to this. Does that make sense? Any questions on that one? So we've got this guy. We just figured out the circled entry, so I might as well put it in there. It turned out to be e to the minus lambda t. So most of these we expect to be a function of t. The 4 easy ones involving going down, we already saw were just constants. Any questions? Well, let's keep going. The next thing to do is P01. So to do P01, I claim that means solving this equation. Well, let's see why. Go back up to the forward equations. This time we're looking at this entry here. P01 prime of t. And that would be found by doing what over here? That would be found by taking this row and multiplying it by term, the second column. So let's see if we can do that. Maybe we can squeeze it in here because it's nice to have this thing in front of us. P01 of t, P01 of t prime would be equal to this entry times this one, which should be e to the minus lambda t. Then it would be this one times this minus the lambda P01 of t. And then it would be this one times this 0, which is gone. So the equation that involves P01 is this one right here. And I got it from the matrix because the second entry here would be found by taking the first row and multiplying it by the second column, term by term appropriately. Okay, so that's where this is coming from the forward equations. And that was down here. And so that's a differential equation. We can, if you like, I think I did it over here, let y be P01 of t, because it's just, well, that's actually even a little too simple. It's really what? It's really y of t. Okay, so using that, well, I guess I never really used it. What I did use, I called it f. So let's go over here and call this f instead of y. Let f of t be equal to P01 of t. Okay. So if you put that into this equation, you get Well, okay, you can take this equation, and which is, oh, this equation, you could put in P00 t because we just figured that out. That was e to the minus lambda t. And I think that already was in play up here. Yeah, e to the minus lambda t was there. So this second equation holds. And now you can bring this term to the left side. And if you do, you get this equation. So now you have one equation involving one function. The function is P01 of t, but if you call f that function, then this becomes this. Okay, and that's the one that the authors did on page 92. So if you have a first order linear constant coefficient differential equation, this thing has a solution, and we could actually write it out. And I'm turning back to page 92 just to write it out. Well, actually, it's easier just to flip back one page because I had it on the previous page, I think. In theory, it's easy to go back one page. There it is, this guy. So yeah, that was the equation. And now we really want to just apply it. I'm trying to see how I can do this. Yeah, let's just bring it over to the next page. So the solution is f of t equals e to the minus alpha t f0 plus e to the minus alpha t integral from 0 to t of e to the alpha s g of s yes. Okay, so when you have an equation that looks like this, and again, this is on page 92, it's what we did just a few minutes ago. That's how to find the f of t. Okay, and f of t, remember, is P01 of t, so that's why we're interested in this. Okay, so let's put everything in here that we have. I guess the thing we need to realize is in this equation, alpha is being playing the role of lambda. So off to the side, alpha equals lambda. And we already said that f of t is P01 of t. So we can put that in here. P01 of t is e to the minus alpha t. And then we have to find out what f0 is. Well, f0 can be found from this. Just put it in t equals 0. So f0 would be the probability of going from 0 to 1 in no time at all. But that's our initial values, which we already discussed. So if you're starting at 0 and you want to go to 1, but you don't have any time to do it, we agree to call that 0. If you were going from one state back to itself, then we agree to call that 1. You could do it in no time and just stay where you are. But if you're actually trying to transition from one state to a different one, you need some time to do it. So that's 0. And that's what? That's f of 0. So what does that mean? That means this term here is gone. So I don't have to worry about the first thing being this. And so our whole answer is here. And alpha is lambda, so it's e to the minus lambda t is out front, integral from 0 to t. And then what are we putting in here? Well, again, alpha is lambda, so that's e to the lambda s. And g of s, what was g of s? And g of s in this case was what's on the right side. And what was on the right side here is this lambda e to the minus lambda t. Okay, so, but we don't want it in terms of t, we want it in terms of s, so it's lambda e to the minus lambda of s, yes. Okay, that's what g is, it's one on the right side of the equation, and the right side of the equation in this case is this guy. We have to change the t to s. Okay, now the good news is e to the minus lambda t times e to the minus e to the lambda t, try it again, e to the lambda s times, everything here is multiplying, times e to the minus lambda s, there the exponents add, and you get e to the 0, which is 1. So this just becomes e to the minus lambda t, integrating from 0 to t of just lambda ds. And that is not hard to integrate. Just take the constant out. And integrate 1 ds, you'll just get s, evaluated between 0 and t. When you put in 0, everything goes away. When you put in t, you get something. You might as well move the t over here. You actually get lambda t e to the minus lambda t. And what is that all equal to? P0 is 1 of t. Okay, so we're making progress. We have now found P01 of t. And what did we find it equal to? We found it equal to lambda t e to the minus lambda t. So we can put that in here. Lambda t e to the minus lambda t. Okay, we are making progress slowly but surely. We have 1, 2, 3, 4, 5, 6 of the 9 probability functions that we're after. 4 of them were constants, so that was easy, but the last 2, this one we got using separation of variables, and this one we got using the stuff in the book that we just covered, the first order linear constant coefficient differential equation. Why don't we do one more, and then I'll leave the last 2 for you. So I'll go for this one. And then these are yours, homework. Okay. Okay, so any questions thus far? If you're sitting there thinking, boy, this course has taken a turn, you're absolutely right. Why? We're solving systems of differential equations, okay? And we weren't doing that just, like a week ago. We've just been doing it the last couple of days. All right, let's go for P02 of t. Well, that would be this one here. So how would this forward equation give us an equation to solve for P02 of t? It would say P02 of t prime. Let's see if I can write it somewhere in here. How about if I move the picture up out of my way? Yeah, maybe. So I'm saying P02 t prime. That's this entry in this box here. And how would you get that? You would get that by multiplying this row times what? The last column? Because that's the product you do to get the entry in this right corner box. Well, the good news is if you do that, you'll have e to the minus lambda t times 0. That goes away. And then you'll have this expression here, which we just figured out, times lambda. So what does that equal to? That looks like lambda squared t e to the minus lambda t. I think so. And then what else? This guy times 0, which is gone. Okay, so what's the good news? The good news is to find P02 of t, it's not even a differential equation. We know the derivative of it equals this. We just need to integrate both sides, right? So does everyone see how I got the equation? I multiplied the first row here by the first column there. You sort of need to know how to do that because the next two are yours, right? Okay, so in this case, let me just move this down to where I have a little more room. So down here, P02t prime was lambda squared t e to the minus lambda t. I better go back and make sure I copied that down right.
Professor, shouldn't it be lambda squared plus lambda e to the negative?
Let me see where you're at. So you're saying this is off a little bit. I'm doing this times this. Is that what you're doing?
Yeah. So shouldn't the lambda be distributed to the e also, or?
Oh, no. Oh, no. It's just lambda times this thing. And there's, maybe you're thinking of the t to be a plus.
Oh, I thought that was okay. Yeah, I'm sorry. I thought that was a plus sign.
Yeah, if it were a plus, you'd be right. Okay. But it's a t. So you're just multiplying this by lambda. But thank you anyway for this, for the thought. So I think we're okay. And let's see, did I write it down right? That's why I was going up here to begin with. I think I did. Yeah, here we go. All right. So now what does it come down to? We just want to integrate this. So, so P0t would be found just by integrating. So what we need to do, we could just integrate this. Yeah, okay. So we need to integrate this thing. Okay. Now, if I wanted to, I could change the t's to s's and integrate from 0 to t. But I'm trying to avoid that. I'm just keeping it in terms of t, and I'll just do a general antiderivative. So if we want the antiderivative of this, the good news is we can move the lambda outside. Lambda squared, because that's a constant. And now you're back in calc, and somebody says, we need to integrate t e to the minus lambda t. What am I hoping you'd say? I'm hoping you'd say parts. Okay, so I'm sorry, it's a lot of calculus stuff coming up here. Integration by parts. Probably you know that as integrating u dv is uv minus what, v du? That's the common parts formula. And so you need a product here, and there is a product. So what I think works just from past experience is to let u be equal to t and let dv equal everything else. And if you take the u dt, you'll just get 1, which means du is the same as dt. And if you divide both sides by dt here, dv dt, This is e to the minus lambda t. And you need to know what v is. So I need to know to integrate this, I would just get v. If you integrate this, it's an exponential, so it's almost itself. I would do that with guess and check. My first guess would be e to the minus lambda t. But if you differentiate this, you'll get this times minus lambda. So that's not what you want. You want this. So I think my second guess would be this. Let me see if we believe all that. So if I differentiate this with respect to t, the minus lambda on the bottom is a constant, it'll just stay there. I'll get this, and then a minus lambda will come out by the chain rule. And the lambdas, minus lambdas will cancel. So I think this is good. I need this because I needed to know what u is and what dv is. I started with that. And in the end, I need to know how the du is related to dt, and I need to know how v is related to this stuff. So I think we're okay. So let's put all of that into here and see what comes out. So u is equal to t. And v, according to this, is equal to this guy. So that's e to the minus lambda t all over what? Minus lambda. So that's the uv minus v to u. I need a little room. Move this away. So my v is equal to this. And my du is dt. Okay. Now, yeah, let's see what happens here. If you well, I guess I can simplify this part. Just put a minus in front of t e to the minus lambda t, and there's a lambda on the bottom. And here the two minuses would cancel. And when I do that, I'm just integrating e to the minus lambda t. But that's going to be minus e to the minus lambda t. You know, just make, I think it's just plus actually. Plus over lambda. Something like that. Let's see, let's double check. So this one, yeah, maybe getting into trouble by not putting everything in terms of s. Maybe. Yeah, let me go slower. So where were we? We were at this stage when we wanted to go parts. And I think, yeah, because we're here. So let's go over this, but let's do it slower. Let's replace all the t's by s. So if I replace all the t's by s, it would be in here. Yeah, let me replace it right in here. So it would be P02 prime of S is equal to lambda squared S e to the minus lambda S. Okay, so do that equation. And why am I doing that? Because I'm going to integrate. So if I integrate both sides, so I'm going from here to here. And then from here, I'm integrating both sides. So I'm going to integrate. Integrate the left, I'd have 0 to 2 prime of s ds from 0 to t. And integrating the right side, we'd have 0 to t lambda squared s e to the minus lambda s ds. Okay, so I'm going to erase this. I'm still going to use parts. But in a minute. Okay, so a little bit of a redo. This equation here, which is the derivative of what I want, is equal to this. I just wrote in terms of s. And then I'm integrating with respect to s and evaluating from 0 to t. Okay, so what do you get? On the left side, you would get the integral of the derivative is just the function. Evaluated at s and evaluated when s is 0 and when s is t. And what is that? Well, when s is t, you just get p02 of t, which is what you want. But when s is 0, you get minus p0 of 0. So the left side of this equation is this. Now we can simplify this a little further because of our initial values. This is going from 0 to 2 in no time at all. So by our initial value, this would just be p02 of t. Okay, so by integrating this, I do get what I want. And now this equals the integral on the right side, which is 0 to t lambda squared s e to the minus lambda s ds. Are we still together? I hope. Okay. Now to do this integral is what I need. If I can find this integral, then I've got p02 of t, and that's what I'm after, right? Because I'm after this guy, p02 of t. Okay, so now we got to play on the right. So to do this, we can factor out. So let's just worry about this guy right now. This is what we need to figure out. What is that? What you can do is take the lambda outside, and you're integrating from 0 to t of s e to the minus lambda s ds. Okay, and here's where I want to use parts. So I want to do what we did before. Here's the parts formula. I want to let u equal s and let dv equal this part. And if that looks familiar, it is. It's what I erased before, but now I'm in terms of s rather than t. So if I do this again, du ds, I would just get 1, which means du is equal to ds. And on the other hand, dv ds is equal to this. So in order to find v, I have to integrate this. And I'm claiming integrating this would just be e to the minus lambda s all over what? Minus s. It's easy enough to check. If you differentiate this with respect to s, the bottom just stays there as a constant. You get this, and then you get the minus lambda coming out. So what I want on the bottom is not s, but what? Minus lambda. Right, again, if I differentiate this with respect to s, the constant on the bottom stays there. You get this, and then you get a minus lambda popping out, which cancels it, and then you get what you want. Okay, so now we're set up to do parts one more time. So what do we get? We have, you know what, why don't we just do it for this part of it? And we'll just remember there's a lambda squared times everything. So we have the integral from 0 to t of s e to the minus lambda s ds. And that equals u, which is s. I'm using the parts formula now, which is up here, which is u, which is s, times v, which is all of this stuff, e to the minus lambda s minus the lambda. But when you have limits here, the limits go here as well. This is for s going from 0 to where? To t. I think I'm doing this right. This is the uv part. But I actually, when you have limits, which we sort of do, like a to b here, you put the limits here, and you put the limits here as well. So the limits in this case are 0 to t. And then what's left? Minus v. So what's the v? V is all this, e to the minus lambda s over minus lambda. Minus v du, but du is equal to ds. And the limit on the integral is 0 to t. Okay. So it's a big calculus problem. All right, let's see what gives here. So when s is t, the upper limit here becomes t e to the minus lambda t all over minus lambda. That's when s is t. And when s is 0, what do you get? When you put in 0 for s, it just goes away, right? 0 times something is 0. So this is all you get from this part of it. Let me make sure of that. T e to the minus lambda t over lambda. Yeah, that's right. And now what about this integral over here? Well, first of all, lambda is a constant. The minuses cancel, so you can pull the constant out. It's 1 over that constant, and you're just integrating e to the minus lambda s ds. Okay, but we know how to integrate that. You can pretty much do a guess. It would be e to the minus lambda s over what? Minus lambda? Why? Because if you differentiate with respect to s, you'll get this. The constant stays there, and then the derivative of this will give you the minus lambda, and that'll give you this. So this is right. The 1 over lambda up front, and evaluating from s going from where? 0 to t. This has already been evaluated, so we can just leave it as it is. T e to the minus lambda t over minus lambda. Okay. This equals this, which equals this. Now what? Let's see, I hope it's all done right. When you put in s equal t, what do you get? Well, this part is done. So this is t e to the minus lambda t all over minus lambda. Why don't we just put lambda on the bottom and put the minus in front? And this one, when s is t, it looks like you get plus e to the minus lambda t. And then these two products, so you get a lambda squared, and the negative, I guess, can be moved in the middle. Okay. So when you evaluate s equal t, you get this. And when you evaluate s equals 0, what do you get? When s equals 0, it's the lower limit, so you'll get a negative. So that'll take care of this minus lambda squared. But e to the 0 is 1. So it looks like just what? 1 over lambda squared? Okay. Let's see if I did this right. I think maybe I messed up, but I'm not sure. This is all of this. I'm just checking. Yeah, I don't see anything wrong with this one. And I'm checking this one too. I think it's okay. At least I don't see anything wrong with it. Okay, so this, all of this stuff, the integral from s, all of this is equal to this stuff. So what can we do? We could then put, we need to multiply. So our answer here, P02 of t was this. So all we have to do is find out what lambda squared times this is, which means all we have to do is take lambda squared times this stuff. So we need to do lambda squared times all of this stuff. Okay. And what does that give us? Lambda squared times this will just give us a minus e to the minus lambda t. Lambda squared times this will just give us a 1. And lambda squared times this will give us a minus t e to the minus lambda t times the lambda, right? Yeah, one of the lambdas cancel, the other one's still there. Okay, so I think we're getting this, which is equal to this, which was equal to this, which is P02 of t. So we're getting this. P02 of t equals this guy. You can clean it up a little bit. These two have the same e to the minus lambda t in it. So you could write this as 1 minus, or is it 1 plus lambda e to the minus lambda t. Okay, so that's what we're getting for P02 of t. Not fun because it's parts. Now, it would be nice to be able to check whether this is right. Let me see. So we think we know this guy, which is the one I said I would do. And I think it's this. Oh, I lost a t. My bad. So when I factored out the e to the minus lambda t, it should be 1 plus lambda t. So there should be a t in here. Okay. Well, this is done somewhere in the book, so I should be able to check it. Somewhere they do pure birth. Oh, okay. I think it's in section, page 94. Oh, but it'll take a bit to check. Well, maybe there's another way to check. What would be the other way to check? Oh, you're not going to like it. Actually, I don't like it. Okay. But I realize now there's a totally much easier way to do this. What's the much easier way to do this? We're trying to find P02 of t, right? And we already found this and this. So what do you know about the sum of this row?
Had to add up to 1. So it's
Yes.
subtracted.
Yes. Oh, all right. So there's a much easier way to do this than what I did. I mean, what did I do? I went through the differential equation. And well, it remains to see if I did it right, okay? But the much easier way to do this is to remember that this is a stochastic matrix. I apologize. Which means if you add everything in this row, it adds up to 1. Okay, so the easier way to do this and avoid parts and everything would be to realize that e to the minus lambda t plus lambda t e to the minus lambda t lambda t e to the minus lambda t plus the one you want adds up to 1. So what does that mean? So P02 of t is 1 minus these two terms. So look how much easier that is. I'm a little, I won't say ashamed, but I wish I'd seen it earlier. Let's put it that way. Okay. So this is our answer. We can factor it out again and check what we got. So we can factor this out, put the minus out in front, and there'd be a 1 plus lambda t e to the minus lambda t. Now the question is that what we got going the long way? I don't know. Going the long way, 1 minus, I think it's the same, thankfully. Okay. So, yeah, this expression here appears to be the same expression that we got using integration by parts down here. So that's the good news. No mistakes apparently have been made, but I found a much easier way to do this. Sorry for the time, but in a way, maybe it's not bad because it's a review of integration by parts. And I think in general, that would come into here. Okay. So I'm way over time, but let me at least clarify the homework. So we found the first row, and I said for homework, you do these two. Now, by the way, once you find this guy, the easy way to get this guy is just to do 1 minus this one, right? If you're a glutton for punishment, you may want to try parts or something like I did, but I don't think you want to do that. So at least learn from my mistake, I suppose. Find one of these, and then the other one is just 1 minus that one. Questions? Sorry for going way over time. I will take a little water break and come back and talk about this or anything else you want to ask me about. So I'll see you in a few minutes, see you in about 20 seconds here for those who are hanging out. For those who are not, have a good weekend before Thanksgiving, before the shortened Thanksgiving week.
Thank you. I actually had a question about that. Do we have class Wednesday morning?
Yeah.
Okay. Thank you.
By the way, I answered yes, because I think we always have. I haven't actually checked this year, but I assume it's still the same.
Yeah, that's actually one of my professors said that we've always had, but because no one shows up, he's canceling his.
Oh, someone is canceling there, so.
Yeah.
No, I need the day. We need the day. We got stuff to do. So, sorry.
No, that's fine. It's an early morning online class, so I'm fine.
Okay. All right. Any questions? I mean, again, I don't know what to say. This whole last part with parts is correct, but as unnecessary. Now, by the way, if we had this problem, suppose we wanted to go one more step up, then it would have been a 4x4 matrix instead of 3x3. And so then there would have been 2 more entries out here, that 0, 2 and 0, 3. And in that case, you couldn't do this sort of this slick answer of just finding this by subtracting the sum of these two from 1. Because if there were another entry and you don't know that wouldn't give you the answer. Which means what? If this were, so I'm trying to tell you that there's some salvation to what we're doing here. If this thing were 4x4, which means if it had one more arrow going up to 3, and we were asked to define this stuff, we would have to do this one pretty much the way we did it with parts, I think. Any questions? Okay. All of this is done, I think, in the book. So let me see if I can point that out to you too. So this is under the section that he calls pure birth processes. Well, actually, it's under section 322, which he calls Poisson processes. And he says, consider a pure birth process where lambda x is always lambda. So it's on page 94 and 95. And I'm trying to see. Yeah, what he's doing there is more general than what we're doing. Um, but if you look at it, well, let me see if it makes some sense. I think it does. So let me just look at what he has and what we have. So actually, it will tell you how to do your homework too, if you want another check for your homework, I think. He's saying that if you want to do Pxx of t, so this would be P00 t in this entry, P11 of t, and so on. He's saying that this one here, well, okay, I got to be careful. His is more general. Okay, what is he doing on this page? So let me at least. So he's doing something similar, but not quite the same. His is a little harder in a way. On page 94, 95, he's doing something called a pure birth process. Okay. However, yeah, he's doing this 0, 1, 2, 3, going on forever. The state space for him is 0, 1, 2, 3, etc. The rates going up are all lambda. Okay, so he's doing that guy. Okay, what are we doing? Sort of a baby version of that guy. We're doing this guy. We just have 3 states. Okay. And it appears, okay, so his is different, but what's going to happen, I think this part of ours the part that goes here is going to agree with the same part for him. But for him, his matrix looks like what? His solution, since it's infinite dimensional. Let me see if I can buy a little space here. Thank you. Thank you. I'll take it. He's got a P of T matrix that looks like this. But it's an infinite by infinite dimensional kind of guy. Okay. So that's the problem he's doing. It's pure birth, but it never stops. So, I mean, that's sort of a little unrealistic, but hey, it's a model. You just keep going up and up forever. And he wants to calculate all of these guys. What I'm suggesting is, I think when he calculates these, I think it's going to coincide with what we did already. Well, not quite already. There's still your homework to do it. But it coincides, I think, to what we were doing here. So what I'm saying is, I think he'll get the same value for the P00T as we did. He's going to get this value again for P01 of T. And let me see if I can just confirm that. I have to look at it a little more closely, but I think that's true. Yes, there it is. So on page 95, he figures out P of x plus 1, and it's always lambda t e to the minus lambda t. So for him, on this one that's infinitely valued, whenever you're going from x to x plus 1, so this is the same as this, is the same as what would be the next one? 3 to 4, which is, yeah. Let's see, 0 to 1, 1 to 2. It should have been 2 to 2. So the next one here should be 2 to 3. So this one, and the next one, which is 2 to 3 of t, are all going to be the same, and they're going to be the same as this, and that's going to be the same as ours. So there's some of this that's in common. But I don't think P02 for him is the same as our P02. Why? Because he's going to have probabilities for all of these things, and our 3 are going to add up to 1, but his whole row is going to add up to 1. So I think the last one's going to be different than ours, even though this one is the same and this is the same. So the first 2 on the first row, I think for him, are the same as ours, which really just think, because look at it, you're just using this part of the diagram. But if you keep going, then there's other stuff out here which affects this. So this one turns into what's called the Poisson process. And we'll talk about it later. We haven't got there yet. But this stuff turns into the Poisson process. You may have seen that already in another class. But this is a way to think of it. It can be thought of as a pure birth process among the Markov processes. Okay, so getting back to your homework, how does this affect the homework at all? Not too much, even though I can use this to sort of check these two. But we'd already done. So now in class, we did the first row, right? Oh, let me see, is that correct? I hope so. Yeah. Because we'd already done 0, 1, we've gotten this, and this is 0, 0. And this, the easy way to do it was over here. So we already have our first row. So as far as the homework goes, I think you're still going to have to do this one. And I think the answer is going to turn out to be this guy. And if that's true, then what would this one be? 1 minus that, right? Because the row here has to add up to 1 as well. So we're sort of finishing off. Where are we at? We have 9 entries here. 4 of them came quick. The first one wasn't bad. The second one was a little harder. The third one I made harder, but it didn't have to be hard. It's just 1 minus these 2. I don't think this is going to be bad. And getting this should be 1 minus that. Questions about how to complete the one that we did started here? Now, if you want, I could actually do 1, 1 for you. Or you might want to just try it yourself. It's either way. Questions on any of this stuff? If you'd like me to do 1, 1, let me know. That would be doing the only homework problem I gave you, but still, I don't care. What could a typical problem like this look like on the final? It would be somewhat easy to tweak. And maybe I'll give you another homework problem to think about. That would be a natural follow-up. So homework, you can call it future homework, but since you're here, I'll probably just formally assign it next time we meet. But instead of this, suppose this is 1, suppose this is 2. Okay, I mean, that looks almost what we just did, right? What we just did, where we had birth, where the rate was always 1. This is harder. Why? Because the rates are not the same. So what could be the question? The question could be find or determine P of t. P of t again would be 0, 0 of t, 0, 1 of t, 0, 2 of t, 1, 0 of t, 1, 1 of t, 1, 2 of t, 2, 0 of t, 2, 1 of t, 2, 2 of t. Okay. So now I haven't gone through this for years, to be honest. Okay. I think it's quite similar to what we just did, what we've been doing in class. After all, the diagram is almost the same. The only difference is this arrow is labeled 2 instead of 1. And to show you why I think it's almost the same, what would come quickly? What would come quickly are the ones that came quickly before. So let's just double down on those and make sure you follow. What's the chance of going from 2 to 0 after a long period of time? There's no way to get back there. That'll be 0. What's the chance of going from 2 to 1 at any point in time? No way to get back, 0. What's the chance of going from 2 to 2? Well, once you're at 2, there's nowhere else to go. You're there forever. So the probability of being at 2 if you start at 2 is 1. You're sort of stuck there. That's the same kind of argument that we gave when both of these rates were 1, right? What about this one? Going from 1 to 0? No can do, right? You're at 1. There's no way to get down there. So once again, if you saw this on the test or homework or wherever you see it, those 4 come quick. What about the remaining ones? Okay, I think, and I'm not positive because I haven't done it for a long time. I think this one is going to be the same as what we just did. Why? Oh, let's see if we have it here. Yeah, here's our P00. How did we find P00? Oh, I'm sorry, this was lambda. Now I'm making lambda 1. Okay, so it's all right. So if lambda was 1, then everything would you just put lambda equal to 1. In the other case, I actually put numbers in 1 and 2, but no matter. If lambda were 1, then the solution for this guy was this. How did that come about? Because P00, which was over here, was equal to this row times this column. And so you quickly got this equation. But that only involves P00. And I don't think that's going to change at all for this problem. So I'm saying, I think the forward equation for P00 is the same here, where lambda equals 1, as it was at the top of this page. So I'm suggesting that this analysis is still spot on. The only difference would be lambda is 1. And so what did you come out with here as an answer? What you came out of here answer is e to the minus lambda t. Okay, so if you want to make it even match closer, I suppose, we could make this, instead of doing numbers, which I think is easier, but if you prefer and you want to compare it with the other one, you could think of it this way. This is lambda, and this is 2 lambda. Okay, now it looks more like the one we did in class, but I sort of like the way I did it anyway. I liked it with lambda equal 1. What am I suggesting? I'm suggesting the answer to this is the same as the one that we had above, which was what? I think it was just P00t was e to the minus lambda of t. Isn't that what it turned out to be? Easy enough to check. Yeah, e to the minus lambda t. Moreover, I think this is the same. Why? How did we find this guy? This is P01 of t. P01 of t was found by getting from this equation, right? But notice this equation just involves P01 and P00. P00 we already said is the same as in either case. So I think the equation for P01 just involves P01. So I think what we did before, which is all of this stuff, is going to work out the same. So I think this answer, this answer is the same. I believe. Yeah, now we believe that. if this is the same as what we had before, and I'm not as sure, it's lambda t to the minus this stuff. So I suspect this one is going to be the same as we did before. So somewhere there's got to be a difference here because there is a 2 here and there's a lambda there. So what? But if we believe what I just said before, that to get this one, you just this sum, this one, and this one sum up to 1, then this would be 1 minus that. Okay, so now this is beginning to look a little too good to be true. Why? Because the first row is the same as it is before. We believe everything I've said so far. So I'm not sure I buy that. Because the 2 here should make a difference in some manner, and it's looking like I'm not making a difference anywhere. So I'm beginning to question whether this one is true. Why don't we look at that a little closer? So how do you get the equation for 0, 1 t? Let's go back and look at that more closely. Because it's all here. So for 0, 1 t, we got this equation. But let's see how it comes about. That's where it comes up. This thing is not the same. How does this thing change? Okay, so that's let's go back to this. Let's look at this. How would Q look? Q would look like the chance of the rate going from 0 to 1 would be lambda. The rate going from 0 to 2 would still be 0. So the rate, this is still here. So far, no change. From 1 to 0 can't happen. From 1 to 2, there's the change. That would be 2 lambda. And so what would this be? Minus 2 lambda. Okay. And then how would the Q change for 2? From 2 to 0 is nothing. 2 to 1 is nothing. And this would be this. Okay, so the Q matrix does change. Mainly in here, right? Because instead of having minus lambda and lambda, we have minus 2 lambda and 2 lambda. And is that going to affect us? Yes. So I take this part back right up here. I now think this one, well, I think this one is still the same, but I think P0T would be different. Why? Because the equation oops. Here's the difference. And this is equal to P00 prime, P01 prime, P02 prime. And these others are what they are. I just don't need to fill it in. Okay, so how would you get the equation for P01 of t? 01 prime of t would be achieved from the forward equation by multiplying this times this. And when you do that now, you're going to get lambda times this one. And then you're going to get minus 2 lambda times the P01 of t. And that's different than it was before because of the 2. Okay, so if you do this homework problem, it will be very similar to what we just did, but there will be a 2 here instead of a 1, which I think will make this different. No longer the same as it was before. And that will make this different. I'm not sure if this is going to be the same as that. So, but I think these will be different. These two. Because this equation is slightly different, it has a 2 in front of that instead of a 1. So this is a decent follow-up problem to what we did. Why? Because it's almost the same, except the rate of going from 1 to 2 is twice the rate of going from 0 to 1, whatever that might be. Does this homework problem make sense? I'm not saying the answer is obvious, but does the problem make sense? It should be thought of as a natural follow-up to the one I did in class. Questions? Do you want me to do part of this or part of the other? I don't mind. But
Hey, Professor,
yeah,
I wanted to ask if you looked a little bit more at that one problem we were talking about.
let me see who's talking.
It's Raymond.
Oh, there you are, Raymond. I didn't see you earlier. Yeah. I've thought about it, yes. And I do have something I could talk to you about on that. You're talking about the problem that having to do with the rank of the matrix, right?
Yes.
Yeah, I have thought about that. And if the session is coming to an end, can you hang a few minutes afterwards? So I'll just talk to you about that individually.
Yeah, that'll work.
Sounds good. But before getting off on individual kind of issues like that, anyone have questions about what I'm doing here? Let me see who else is with me still. Well, again, I'll make the offer, but I'm not hearing anyone say yeah. So maybe you're okay. Maybe you're just, look, I think we did a pretty thorough job of doing this one. So I don't feel, other than seeing the easy way to do it, I don't feel bad about what we did at all. And in fact, I'm very thankful that we did it, even though we did it the long way. It's at least you got to see integration by parts again, which is probably not a bad thing to show you. Okay, so why don't we leave it where it is? So where's the homework? What should you be doing? We did this, and this. We did this one 2 ways, a long way and a hard way. And I'm asking you to do these 2. And I'm also telling you that if you do this one should be almost immediate because the sum of the rows should be 1. So it'd be 1 minus the other. So that's the homework. And then we have another follow-up homework, which you consider future homework, but you know, it's coming sooner or later. So you have a little head start here. This one here, if you simply put a 2 here instead of a 1, how does that alter all of these guys? I suspect this one doesn't change. I suspect these 2 do. And well, the other parts I've already put in. If this is indeed the same as that, which it may be, not sure, then this would just be 1 minus, whatever this is, this would just be 1 minus this. So in a sense, this problem has three different ones to figure out. This one, and this one. Because once you figure out this one, this will be one minus it. Similarly, once you figure out this one, this will be one minus it. So there's really only two that you got to wrestle with. This one and this one. All right. So it looks like you're giving me a break. I'll take the break and I'll let you free, except for Raymond. Anyone else have any other specific questions?
No.
I hear a little bit of background, but nothing I can make out. Maybe.
I'll see you next week, Professor.
All right, Candace. Thanks. Good luck with your new computer.
Yeah, thanks.
It'll be a headache until you figure it out, but you'll get there. Okay, so let me see. I'm left with Ricky, Raymond, and Hugo. Do you guys want to hear about Raymond's technical question? If you do, you're welcome to stay with us. And if not, you're welcome to start your weekend or whatever comes next now.
I'll see you in a bit, Professor. Bye.
Okay.